Okay, here's a quick review of some kinematics and some motion equations. Alright, first let's look at the graphs. Alright, there's the graph of displacement against time. As you can see, the gradient by ds by dt would end up giving us the velocity, so I can write that like that. Displacement against time, differentiate it with respect to time, and we end up with velocity. Alright. Now, moving down to the velocity time graph, I can see the gradient here is dv over dt. Now, if I come back to this, we know if I differentiate velocity with respect to time, I end up with acceleration. So there's the two ways we can differentiate displacement and end up with velocity, and we can differentiate velocity and end up with acceleration. Now, let's look at a graph of acceleration against time. Now we know that acceleration equals velocity over time. Therefore, if I rearrange that equation, velocity equals acceleration times time. You can see acceleration times time is the area under that graph. Now, if I integrate area with respect to time, I'll end up back at velocity, alright? Because integration is just like finding the area under a graph. Now let's come back to our velocity time graph. Velocity and time. Now if I look at the area underneath that line, it's going to be velocity times time. Now, the original equation is velocity equals displacement over time. So displacement equals velocity times time. Now, velocity times time is the area under that graph. Now, to do areas under a graph, we integrate again. So if I take a velocity function and integrate it with respect to time, I'll end up back at displacement again. So you can see that sequence here, how each of these are linked to each other through differentiation going that way and integration going back. And they completely tie in with these three displacement time graphs, velocity time graphs and acceleration time graphs.